Good afternoon. Welcome to Mechanisms and Machines. If you haven't yet noticed, I let you know that I love dynamics. Okay? So I really think or agree with what other people are saying, that dynamics is the most important intellectual discipline of humankind, right? And of course, maybe like a generally understood term, dynamics as a science of or studies of systems undergoing change of state. I mean, this is very broad, and we will confine ourselves to mechanical systems, right? But still a very interesting discipline. And I suppose it's hard to be a mechanical engineer without knowing mechanics, right? Maybe you can be a project manager without knowing mechanics. But before you become a project manager, maybe you will have to display some knowledge of mechanics in your career, and even in a few more years you have before you graduate. Okay, so nomenclature, I think the most straightforward nomenclature which I like is that mechanics is split into statics and dynamics, right? And statics is when things don't move, so this is civil engineering stuff. And dynamics is when the things are moving. And another thing a bit separate is kinematics, which we discussed at the beginning of the semester, which is the geometry of motion, right? So forces of no interest. Okay, so the universe is dynamical. And it was the science of dynamics that gave us this understanding of the evolution of the universe, and consequently gave us the understanding of our place in the big picture of things, right? So it took a few thousand years to figure out, but now we will look at a little bit simpler case than the universe. This is a gyroscopic grinding mill. Okay? We will have a movie even, so you can see how it works, right? So you have two heavy rollers, okay, which roll on top of inside the bucket. And then at the bottom of the bucket, there is something to be crushed. Maybe some stones and rocks that need to be crushed to some smaller fraction pieces, or maybe olives, and we want to produce olive oil and things like this, right? So we have two heavy rollers, or sometimes called mullers, rolling and crushing stuff at the bottom of the bucket. Now, the question is, of course, we want a large force to crush what we are crushing. Right? So the question is the crushing force, which is the force between the rocks or the bottom of the bucket and the rollers, is the force equal to the weight of the rollers, or not equal and maybe smaller or bigger? What do you think? Sorry? Not equal, smaller or bigger? Well, if you go and Google this thing up, it's called a gyroscopic grinding mill, you will find many different types. So people are building these things probably because the force is bigger. So it crushes the rocks better than just the weight of the rollers. So we will use this case study analysis of the motion and of forces involved of this machine as a pretext to consider 3D dynamics. Okay, I am betting you have not done anything or seen anything dynamical in 3D in your education so far. I think all dynamics you have seen was either a point mass or something in 2D, right? Even the kinematics we have done, almost all examples I was showing were planar mechanisms, right? So now the 3D stuff is starting, and it is very scary. Okay, so this was the video, and this is actually the view. This is a bit too small. Let us view, zoom. Okay, so we have here the sketch of one roller. Okay, in the machines you have seen, the angle theta there was 90 degrees, right? So the axis of rotation of the roller was perpendicular to the vertical axis around which everything rotated, right? But of course, generally speaking, it can be at the angle theta, and we will actually look for angle theta that maximizes the crushing force. Okay? So we will look at this problem as a design case study. Our design variable will be theta, and we want to find theta so that we maximize the crushing force. Okay? So we already answered the first question. The so-called mysterious gyroscopic effect will make the force larger than just the weight of the rollers. And of course, this is a 3D motion, right? Because it's not happening in parallel planes, so it is a general 3D motion. Okay? Now, the truth is that it is not 100% general 3D motion. It has one small aspect that makes analysis simpler. So this is the motion with one point fixed, right? So point O, about which we have a complicated three-dimensional rotation, is the fixed point of this motion. Okay? So unfortunately, the absolute general treatment of 3D dynamics is beyond the scope of undergraduate course, but a slightly simplified special case with one 3D motion with one point fixed, I think is within our capabilities to learn and then get examined at the end of the semester. Okay, so well, there is a long history of people dealing with dynamics, starting from ancient Egyptians via ancient Greeks to, say, Renaissance people like Galileo, right? The interesting thing is that until Newton, everybody considered that the extraterrestrial motion is something different to terrestrial motion. Okay, so the motion on Earth was considered a different thing than the motion of stars or planets. So it's only Newton who came up with dynamical laws which unified terrestrial and extraterrestrial motion as one thing. And then after Newton and Euler, something called the direct approach to dynamics was developed. And the direct approach is what you are used to, because this is the direct, or using different terminology, vectorial approach or momentum-based approach, as opposed to indirect approach, which unfortunately is not covered much in our curriculum. There will be a unit given by G. Pan at the first year of masters, which will hint on some indirect approaches. Okay, so we will be doing the direct approach, and this is, of course, Newton's stuff. How did he look like? Looked scary, didn't he? Right? So he actually, during his lifetime, he actually entered a number of serious controversies with his contemporaries. Includes Hooke, the one from law of elasticity, and Leibniz, where this is the most famous controversy about the, say, who was the first to invent or discover calculus, right? So these are pretty funny stories, and you can find the literature about these controversies, which sort of give a gist of how science is really affected by normal kind of social interactions, and how even the development of science can be distorted or diverted by some personal problems or animosities. Okay? So these are the Newton's laws. 1687 translation. Translation from what to what? From Latin to English. Right? At that time, everyone was using Latin as the language of science. So the first law, obviously, no force, no acceleration, or so the particle moving or body moving along the straight line with constant velocity. Can you imagine that Aristotle proclaimed that to maintain the motion, the force is needed, and this incorrect view has been considered true for over 2,000 years, right? So it's only Galileo who disproved Aristotle's view on, say, what's needed to maintain the motion of a body. So second one, force proportional to the acceleration, and third one, of course, action equal to reaction. So this is all we know very well, but I'd like to bring to your attention that these laws, Newton's so-called Newton's laws, are not really that fundamental, because they apply to a phenomenally simple physical model, which is a point mass. Okay? So anything that is not point mass is not a subject to Newton's laws. Okay? Because Newton's laws are for an idealized system, which is a point mass. So what if we have a mechanism which is, of course, has contains a number of links which are rigid bodies, right? So we need to consider what are the fundamental laws for rigid bodies or extended bodies. So we have a picture taken from the handout. So we can consider a rigid body as something which would have some center of mass, right? And it would have, say, at every point we could idealize it as that every point contains maybe some small mass mi, right? And then the properties of the rigid body would be the sum of the properties of all these masses around the body. So we can consider this mathematically as a sum, but we may also use integrals over volumes to take into account that this is a continuous body. Okay? So now the fundamental quantities that are used to describe the behavior of, or the motion of an extended body is the momentum and angular momentum. Okay? So momentum for a particle is just mass times velocity, right? But for an extended body, it would be the sum or integral over the volume of all these masses and velocities. And luckily for us, this is equal to the mass of the entire body times the velocity of the center of mass. Okay? So this green thing looks very similar to the equation for the particle, right? Because for the particle, momentum is the mass of the particle times velocity of the particle. So if we didn't look at this, we would perhaps begin to think that Newton's laws actually apply to that body as well, because it looks the same as the particle. Well, but for the body, the situation is more complicated, because a particle, a point mass, at least within the context of classical mechanics, cannot rotate. There is no way to describe the rotation of a point. Actually, in quantum mechanics there is, but we don't need to worry about it. It's the classical mechanics we are talking about. But of course, rigid bodies rotate. So you have one more important quantity which describes the motion of the rigid body, which is the angular momentum. Okay, so I use symbol, so it's a vector. I use most of the time symbol capital H, as in the purple book. Okay, but well, notation is of secondary importance. So this is so angular momentum or moment of momentum. So moment of momentum for a single particle is just the radius cross product the momentum, right? And then for the extended body, it will be a sum or integral over the entire body, right? So these are the things, and we can have it here again. So momentum and angular momentum. Angular momentum around the center of the coordinate system, O. Okay? And the red stuff are actually fundamental laws of nature. Not Newton's laws, but the red stuff here, which is the conservation of the momentum principle, that the momentum of a system, of the isolated system, remains constant. And as far as I can say, nowhere in the universe at the largest or the smallest scales a violation of this has ever been found. Okay, so this goes far beyond rigid body mechanics. It's stars, it's electrons, it's anything. Okay? And similarly, the angular momentum principle. So the angular momentum for an isolated system remains constant. And again, this is a fundamental law of nature which has never been found to be violated anyway. And it is an independent law from the first one. Okay? So these two laws are independent. And this may require perhaps a little bit of explanation, Because you see, if you look just at the particle, so if you have a particle at certain radius r going with certain velocity v and some force F acting on it, you have Newton's second law. Okay, so derivative of momentum equals to force. But if you multiply both sides by the radius, vector product, you get derivative of the angular momentum equal to external torque. So for the particle, these red things are not independent. So the second follows from the first. Okay? But it is only for a particle. For anything that is not a particle, these are actually independent laws, and both of them need to be considered simultaneously when dealing with the dynamics of the system. Okay, so for the particle, you choose this one or this one, whichever is more convenient. But for the rigid body, you need both. Okay? So the red ones are laws of nature, rock solid, and then the dynamical laws that govern the evolution of the system are the blue ones. So the derivative of the momentum equals to the sum of forces acting on the system, and the derivative of the angular momentum is equal to the sum of external moments acting on the system. Okay? Now, if we look at this green one, okay, sometimes we don't want to write our equation around the center, but around some other point. So if we are interested in torques acting about some other point, this blue equation becomes this one. I give it without proof. It's in every book, including the purple book. So this is the correction. But very commonly, this point, which is not the center, is convenient to choose as the center of mass. Okay? And then, as it happens, this red equation becomes, for practical purposes, the same as the blue equation. So if we consider torques acting around the center of mass, it's the derivative of the angular momentum taken about the center of mass, and it looks the same as when we do the torques and the angular momentum around the center of the coordinate system. So actually, in practice, it's most unusual to use this general green equation. You usually end up with one of these two. Any questions so far? Yes, please. Yes. The last three are saying the same thing. Okay, so the blue one is angular momentum around the center of the coordinate system related to the change in the angular momentum related to the sum of moments around the center of coordinate system. The green equation is the same, except that now it's about arbitrary point B. Okay? And the red one is when point B is the center of mass. Okay? And in practice, we deal with blue or red, because this arbitrary point B, what can it be? Most of the time, we will take it as the center of mass. Okay? But the main thing is that these two blue equations are independent. And you need both sets to do the dynamics for the rigid body. This one and this one. And this is different to a particle when you can choose which one is more convenient, because they can be derived from each other. Now, of course, our gyroscopic grinding mill, as well as some aircraft in the air and other things moving in space, rotates, right? So we need to remind ourselves a little bit what the angular velocity is, right? So we talked about it while doing kinematics. I just remind you that the vector of angular velocity in 3D is something like this, right? So direction is along the instantaneous axis of rotation. The magnitude is just the speed of rotation, and then the arrow is decided according to right-hand rule. So in this picture, the body is rotating around this axis like this, right? Right-hand rule. Okay, so this is the rough definition or explanation of what a vector of angular velocity is. Okay, and luckily it's a vector. Now, this is what you have seen many times in the past. If you have fixed axis and rotation in just one plane, so this is a 2D case, which you have seen many times from starting from year 3 in primary school, right? So then the vector of angular velocity will be pointing like along the z-axis, right? Like this. And doing the rotation like this. So would have components 0, 0, and omega in z direction, right? So in a 2D context, it is okay to even treat angular velocity as a scalar, right? You had just omega as a scalar, take the derivative, get acceleration, integrate, get the angle, things like this, piece of cake. Not anymore in 3D, because you remember I told you when doing kinematics that while velocity really is a velocity, because if you integrate velocity, you get position, angular velocity is not really the velocity of any kind, because when you integrate angular velocity, you get nothing. Okay? So angular velocity is not a derivative of anything. Okay, there is no set of angles whose derivative would be the angular velocity. That's why in books thick enough, omega is not even called a velocity, but quasi-velocity. Because they demand that for something to be called velocity, it must be a derivative of something. Okay? Some measure of position of some kind. But angular velocity is not. And this is one of the reasons why 3D dynamics is usually not in the curriculum of undergraduate engineering courses around the world, because this causes serious difficulties when you want to do any calculations. Okay? So, we know what the momentum is. We sort of know what the angular momentum is, right? We know now 2 laws of nature and the dynamical laws. Derivative of momentum is force. Derivative of angular momentum is external moment or torque. We know that in 3D we will encounter trouble with these rotations. We can maybe have a look at the table from the handout. Okay, so this is taken from the purple book. And this is the summary of basic facts. Okay, so essentially nothing in these facts here is really new to you, but let us spend a few minutes just examining the situation. So we have particle, we can have system of particles or the continuum. So we are really interested in rigid bodies, so which is this last line. So for the particle, obviously force is derivative of momentum, or as I showed you on this picture or this slide, if we multiply this equation by the radius, I mean cross product, we are getting this, and that's why we have or here. We can use this or this depending on what's more convenient in a given case, because for a particle these laws are not independent. Okay, and then we have special cases when this point B, I remind you from the picture, is some arbitrary point around which we think it's convenient to take our moments and torques, right? So the important case is that when this point B is a fixed point of motion, okay? So velocity of this point is equal to 0. And this is the case for our gyroscopic grinding mill, right? When we will have one point there at the intersection of axes which doesn't move, okay? So this is an important case. And the second case, important case, is when point B is the center of mass. In both cases, this green stuff here goes away, so we have slightly simplified equations. Okay? So, for the extended body, we have the sum of forces equals to this, and the sum of torques equal to this, but in both special cases, this additional term goes away. So, case 1 is when the point B doesn't move, and case 2 is when point B is the center of mass. Okay? So this is the summary of the theory, really. But a little more work is needed to actually apply the theory in practical cases. And as I mentioned, the general three-dimensional motion may be a bit too hard. So let us look at the situation when we have a general motion, but with one point fixed, okay? Which is actually the situation we have here. Okay, because point O here, while this thing is rotating, is a fixed point of motion. Okay? So we have the situation that this is a rigid body which is rotating with angular velocity omega and moving in such a way that nevertheless there is one point fixed. And in this situation, we have in dynamics these equations to consider. Okay? Sum of forces equals to the derivative of momentum, and sum of torques equal to the derivative of the angular momentum. So we can probably see that to actually make use of these equations, we need to figure out how to take these derivatives, right? The derivatives on the right side to relate the motion to the external forces. What do I have here in the notes? So let us have a look at what's happening in this funny situation. So imagine a bicycle wheel spinning rapidly, suspended on a string, as shown in the picture. Okay, so the wheel is spinning rapidly, right? And is suspended by the spring, and it looks like this from the front and like this from the side. Okay, so angular velocity lowercase omega there is large. Okay, it's spinning rapidly, and the question is, what's going to happen if you just leave it like this? So what do you think? What's going to happen and why? It will. Will it drop or will it do something else? It should stay. But most people normally say that it should drop. So why are you saying that it should stay in this? Because you have seen the lab already. Well, if it didn't spin, right, it would obviously drop, right? So why wouldn't it drop if it's spinning? What makes the difference? Yes. Sorry? It's on the string, but on the side. So if it wouldn't spin, it would just drop like this, right? Right? But the prevailing opinion is that somehow, because it's spinning, it will not drop. So the hope is that after a few lectures on 3D dynamics, we will be able to be very clear in our minds why this thing shouldn't drop. Okay? And let us look at the quick explanation without equations. So you have the situation that it wants to drop, right? So the gravity acting here, the force of gravity, of course, it must be balanced by the force in the spring, right? So the sum of forces must be zero, because if there were the sum of forces were not zero, it would just have acceleration and fly into space somewhere, right? So the weight and the reaction in the spring must be the same. But because they are not acting along the same line, okay, they produce the torque, okay, which acts like this, right? Where is the camera? Like this. Well, too much zoom. So it is the torque which wants to rotate the plane of the wheel in this direction, right? Because the gravity acts here, reaction in the string acts here, so it wants to go like this, okay? But our equations are saying that the torque must be proportional to the change in angular momentum, right? This was one of the blue equations that cannot be escaped. So if the torque does this, it means that the vector of the moment is along the thumb, right? Which means the vector of the moment is along x-axis here, which means the change in angular momentum obviously must be parallel to the torque, because this is what the equation is saying, right? Which means that the angular momentum vector will rotate into the page. right? So we will, instead of this thing falling down, we will have this thing rotating slowly into the page like this, okay? And this is called a precession. So this is the very simple explanation of the gyroscopic effect, okay, or the precession of the gyroscope. We have the thing spinning rapidly around axis Z, with a moment acting along axis X, causing precession around axis Y. Okay, we can even see here the nomenclature. So the Z is the axis of spin, X is so-called torque axis, and Y is a so-called precession axis. Okay, so we now want, in the next few lectures, to come out with quantitative measures and equations that will give us the relationship between forces, velocities, accelerations, and momenta, and angular momenta of everything that's happening. And then we will be able to apply these equations to our case study to actually calculate the crushing force. Okay? So this is the plan. Let me have a look. Yeah, the next thing I have to tell you is so important that I'll defer it to Monday, because I don't want to rush. Okay, thank you.